guys, welcome back STEM superstars. So today we'll be going over the AP Classroom 1.2 to 1.4. These chapters are pretty easy. Just don't overcomplicate them because I will be going pretty quick. I don't want this video to be too long because I don't want to keep you guys, Okay. So first we have to know what is an isotope. So an isotope is just an atom with the same number of protons but a different number of neutrons. Think of them as different versions of the same element. So say you have the element chlorine. Chlorine is not just chlorine. When we think about chlorine, we're actually referring to a bunch of different versions of chlorine all put together into one thing. So like if you look to your right here, we have this mass spectrum of elemental chlorine. This just shows that chlorine, the chlorine that we know of, is made up of chlorine 35 and chlorine 37. Chlorine 35 and chlorine 37 are two different isotopes of chlorine. The only difference between chlorine 35 and chlorine 37 is that they have a different mass number. What do you remember from before? Mass number is protons and neutrons. Protons plus neutrons. We know that in order to have an element, you need to always have the same amount of protons. Just because it's a different isotope does not mean that the amount of protons will change. The only thing that is actually changing is your neutrons. We know that there are always 17 protons in chlorine. So in chlorine 37, there must be 20 neutrons because 20 plus 17 equals 37. While in chlorine 35, there must be 18. That is isotopes explained for you. And another the most important thing about 1.2 is that from the isotopes and how much they exist in nature, you can get the atomic mass of chlorine. Like you can get the atomic mass of the actual element. What this graph is saying to us over here is that we have two different isotopes of chlorine. Chlorine 35 and chlorine 37. With these bar graphs, we're saying that in nature, out of all of the chlorine that exists, about, what is this? This is like, let's say like 77. 77% of it is chlorine 35. The same thing about this. Out of all the chlorine that exists, go right here, it's like 22, it should add to 100. So, let's say like, we'll say it's like 23. 23% of it is chlorine 37. By taking each isotope number, okay, so 35, and then multiplying it by its relative abundance, adding them together, we can get the atomic mass of the element. Notice how this says percent abundance. It's not relative abundance. What we need is relative abundance. Percent abundance is just like if you have like 100 grams of chlorine, 77 grams of it will be chlorine 35 or that, but we actually just need the decimal number of it. So 77% as a decimal is, we just know that we divide that by 100, 0.77 plus 37, and then 23 divided by 100 is 0.23. That is your equation. You can kind of use logic behind this, like, 35%, chlorine 35, 77% of it is this, so in total there will be this much. Chlorine 37, 23% of it exists, in total there will be that much. If you add this together, you'll get approximately 35. And then if you look over here at chlorine, the atomic weight of chlorine is about 35.45. That's how you know that you did it right. And that's how you know that Right. So if we didn't know that this bar set was equal to chlorine, then you could have just done what I did. 35 times percent abundance divided by 100, and then gotten the atomic weight, and then looked at the periodic table, which one of these elements is closest to my atomic weight, and then identified the element. Okay, here's a practice problem. I know it says relative abundance, but I feel like the scale here is very oh wait, I know, I forgot too. A pattern that we can see with this graph is that whatever bar is like the highest will be the number that your atomic weight will like be closest to. So without even having to do this calculation, I could have guessed that the element was chlorine because isotope of 35 was so high, meaning that I can just look at my periodic table, which element has an atomic weight that's closest to 35. I could see chlorine and I'd be like, oh, okay, that's chlorine. That's just a pattern that's there. It's the same thing with this one. I feel like this should say percent abundance, but I did not make this problem, so I will not go into that. But it's the same thing with here. We see that the highest bar is the isotope of 11, meaning logically we can just look in a periodic table what element is closest to, has an atomic weight that's closest to 11, and then just go based off of that. Leave your answers in the comments, and then I'll respond to the comments and see who's right. Okay, that was literally it for 1.2. It was very simple. I told you guys you have this. Okay, now 1.3 is all about elemental composition. So compounds, a thing about compounds, we know that compounds are just made of elements, but in order for a compound to be a compound, it has to have a fixed ratio. Like, for example, if I have AgCl, silver chloride, AgCl has a 1-to-1 ratio, meaning for every 1 Ag, there's going to be 1 Cl. If it was like Ag2Cl, then these are not the same. They're not the same. These are not the same compounds. You can't just say they're the same compounds because they're the same. They have the same elements. They will always have a fixed ratio if you want to say that they're the same compound. Like I said before. Right, okay. So that will always means that no matter what sample of a compound that I have, there will always be a fixed ratio of one element of the compound relative to the other. So if I have 1 mole of silver, like say I have a practice problem, Sally did an elemental composition test or whatever you would call it, and she detected 1 mole of silver. How many moles would you need of, how many moles should there be of Cl? It should say 1, okay? We also know, we can also do this with grams, not just moles. Like how I said before, if you have 1 mole of silver, you will also have 1 mole of chlorine. We know that in 1 mole of silver, there is, we know that in 1 mole of chlorine, there is 35.45 grams. 1 mole of chlorine is 35.45 grams. Okay? That's just how that works. 1 mole of silver is 107.8682 grams. Okay? If you were to put them together, you would get 143.3182 grams. So if you had 1 mole of silver chloride, you would have 143.3182 grams. We know that the chlorine made up 35.45 grams of this. So if you want to put this into a percent, what would you do? Pause the video and think about it. Logically, you can just use algebra for this. You can just do 35.45 over 143.3182 to get 0.247. Multiply that by 100 to get the percent, and you get 24.7% chlorine in your substance. That will always be how it is. Even if you have 300 moles of silver chloride, if you're having a percent by mass, by grams, 24.7% of it will always be chlorine. So this is also something that you can use to really think logically. If I told you that there was a solution, right? If I have a solution, and I told you that it's AgCl, but then you got your magic chlorine tester, and you tested for how much chlorine there is, and it came out to be 30% of chlorine, then you know that there's no way that this is pure AgCl, because it should have came out as 24.7%. That means there must be something else in that solution to make it 30%, something else that includes more chlorine. This is just something that you can think about and something that will help you with the next questions. Practice problems. What's the percent by mass of hydrogen in H2O? And what's the percent by mass of barium and barium nitrate? I will let you guys do this one on your own and then put your answers in the comments. I'll respond to all of them and I'll tell you what you might have done wrong, or we'll go back and forth to see who is right. I will do this one with you though. What is the percent by mass of hydrogen in H2O? We know that if I have 1 mole of H2O, that is equal to 18.02 grams. Right? If I have 1 mole of H2O, then I have 18.02 grams of it. We know that if I have 1 mole of H2O, then I have 2 moles of hydrogen to make up of it. Right? Okay. We have 2 moles of hydrogen to make up of it because it's H2. Okay. 1 mole of hydrogen is 1.01 grams. If I have 2, then it's 2.02 grams. We know that oxygen is 16 grams. 1 mole of oxygen is 16 grams, and there's only 1 because it's only 1 O here. So if you add that together, then you get 18.02. Since 1 mole of H2O is 18.02 grams, and then if you have 1 mole of H2O, you have 2.02 grams of hydrogen, you can do what we did last time. 2.02 divided by 18.02 to get, what do you guys get? I got 0.112098, crazy rounding, but, and then multiply upon 100 to get your percent abundance, and you get approximately 11.21%. Leave a comment down below if you agree with this answer. Again, mistakes are always something that's going to happen, especially in math-based or science-based things. So it's okay to make mistakes, just continue trying. Okay, next is empirical formula and molecular formula. Empirical formula this is a very simple thing. It's just the empirical formula is the simplest form of a compound, and then molecular is any other form of a compound. So remember how I said before that if you have a compound, you are always going to have a set amount of that, like a set ratio. So like if you have AgCl, it's always going to be 1:1. You're always going to have 1 AgCl. You're always going to have 1 silver for 1 chlorine. They're always going to have a constant ratio. We know that this is not equal to Ag2Cl because that's a 2-to-1 ratio. It's not the same thing. However, what if we just increase both of them? Like what if we have Ag2Cl2? That would be equal to AgCl because technically it's still a 1-to-1 ratio. However, you can simplify Ag2Cl2 to AgCl, meaning AgCl is your empirical formula because it's your simplest form of the compound. Whereas this would be your molecular formula, as it's not the simplest form of the compound. Here I have another example, CH2O versus C6H12O6. This would be your molecular. And that would be your empirical, because you can divide all of these things by 6 to get CH2O. What's the empirical formula of H2O2? Well, what did you guys say for that one? What's the empirical formula for H2O2? Just pause the video. Remember, you can divide by 2, you just get HO. Or OH, I don't like the way that, right. What's the empirical formula of C4H10? You can just divide by 2 to get C2H5. You can actually acquire the empirical formula of a substance by using its mass compositions. This sounds kind of weird, but here's what's going to happen. They'll give you the masses of each element found in the compound. Okay, so they're going to tell you, hey, you have this mystery compound, okay? And they're going to tell you each element that's in the compound, and they're going to tell you how many grams that element gives to the compound. So say it's made of like Cl, Ag, and there is this many X amount of grams of Cl and X amount of grams of Ag. You would take the amount of grams of Cl, convert it into moles, grams of Ag, convert it into moles, and then you're going to get a certain amount of moles. You divide by the lowest amount of moles to get the ratios between the two. I'm going to show you what this means because I know this doesn't really make much sense without a practice, like a problem. So here. One of the most commonly used white pigments in paint is a compound of titanium and oxygen that contains 59.9% titanium by mass. Okay, so what they're telling us is that in this compound, we have both titanium and oxygen. We know that we have 59.9% titanium by mass. What does 59.9% titanium really mean? It means that if we had 100 grams of this white pigment, then we would just have 59.9 grams of titanium. So we can just change that to 59.9 grams instead of just ignore the percent part, honestly. If we have 59.9 grams of titanium, then how much will we have of oxygen? Remember, everything always equals to 100%. So that means with oxygen, we're going to have 40.1 grams. We can do simple conversion factor that we learned in, with Zach's previous video, from like the previous video of Zach. And just convert them both into moles. 1 mole grams. How many grams in 1 mole? 16. I do not have the molar mass of titanium memorized, so let's go ahead and look that up. 47.867 is what Google is telling me. So we'll go ahead and do that. So that's 59.9 divided by 47.867 to get 1.25 moles titanium. And then the same thing with this one, 40.1 divided by 16. 2.5 moles. Remember what I said? I said divide by the lowest amount of moles, so you're going to get divided by 1.25. That equals 1. Divided by 1.25. What are you guys going to get? 2. That gives you, what did this give you? This gave you the formula, okay? That means you're going to have 1 Ti with 2 oxygen. And that is your empirical formula. That is your empirical formula. Okay, so let me add to this question really quickly, but you guys are going to have to pay attention to what I'm saying. So say I told you that the molar mass of the compound that we have, the one that you just solved for, but the molar mass of the compound that we have is actually 159.734. But if you solve for this molar mass, you just get, what do you guys get? You only get 79.867. So that doesn't really make any sense. What do you do now? This is where molecular formula comes in. What can you notice about these two numbers and their relationship? Think about it for a second. If you said that they're just, this number is just double this number, you were right. Only thing you would do here is, if this is double, then you would just double that. Ti2O4. And then if you solve for that molar mass, 16 times 4 plus 47.867 times 2, you get 159.734. And that is molecular empirical formula. There's also another thing with hydrates and combustion analysis that you can do with this. It's very similar to what I just did right now, but I want to make a separate video about it because the AP Chem exam kind of takes that really seriously. Lastly, I'm not going to teach this much with this one because I feel like you've learned enough for the past couple of videos so that I don't have to do that. But I'll tell you what this is. So a mixture is the different compounds together. A pure substance is one compound together. So I have a container of just AgCl. That is a pure substance because it's just AgCl. But if I put like NaCl, then that would be a mixture because it would be 2. You can determine how pure of a substance by finding the relative mass of one or more elements in the mixture. Why? Because you should know already what the mass number of an element is in a pure substance. So remember what I said before with, where is it? Yeah, remember what I said before with AgCl and how chlorine will always be 24.7% of it. But if I solved for it in a lab and got 30% of it, then that means it cannot be a pure substance. There has to be something else. That's what that is saying. Use what I taught you to think through this practice problem on your own logically. Okay, so I'm going to read it. A 5-gram sample of a mixture of calcium carbonate and silicon dioxide contains 1.5 grams of Ca. What is the percent of calcium carbonate in the mixture? Okay, so you have a mixture CaCO3 and SiO2 contains 1.5 grams of Ca. What is the percent of CaCO3 in the mixture? This is going to be a little bit of a challenge question, and I'm going to leave you guys up to solving for it. Comment down below what you get and your process of getting there, and I'll respond. Thank you so much for tuning in on this video. Stay tuned for the next video that's going to be posted probably next Monday. Not by me, but by my STEM partner, Zachariah. Okay. Bye-bye. It gets better from here.